In the silence of the early morning, a convoy of trailers moves across the open plains. Inside each one, a force of nature is in motion. Thousands of bulls, each weighing over half a ton, each with a nervous system that reacts to every curve, every vibration, every stoplight. This isn't just animal transport, it's dynamic mass engineering on wheels. Because transporting bulls is not a matter of loading and moving. It's a delicate equilibrium between biology and mechanics, between weight and motion, between control and chaos. Across the world, over 11.4 million live bulls are transported each year. Behind this number is a complex, high-stakes ballet of moving muscle that mirrors an unlikely source: the naval strategies used to stabilize ships at sea. Just like a cargo vessel must manage the rolling mass of its ballast during rough seas, livestock trailers must adapt to something even less predictable: live, breathing cargo that shifts, pushes, leans, and reacts. A single bull can apply hundreds of kilograms of lateral pressure in an instant. Multiply that by dozens of animals, and every corner, every turn becomes a structural test. That's why livestock trailers today are more than just reinforced boxes. They are engineered systems, designed with an understanding of biomechanical load shifts and the unpredictable force vectors generated by animal movement. It's not just about resisting force, it's about absorbing, redirecting, and adapting to it in real time. The comparison to naval ballast is more than poetic. In marine cargo design, liquid ballast tanks are dynamically filled and emptied to counterbalance the tilt and roll of the ship. The logic is simple. To move mass, you must understand how it behaves. And now, that same principle has made its way to the roads. Modern trailers transporting bulls are being equipped with hydraulic tilting beds that respond to animal movement, subtly adjusting the floor angle to prevent pile-ups, reduce falls, and minimize stress. It's not visible from the outside, but under the floor, pistons and pressure regulators are working constantly to maintain internal equilibrium. It's a mechanical choreography in response to biological rhythm. But even that is only part of the challenge. The real stress isn't just the load. It's the fatigue that builds up in the materials. Like the metal hull of a bulk carrier, which faces uneven pressure and eventually wears down, trailers that transport bulls are vulnerable to structural fatigue from uneven axle distribution and repeated stress cycles. It's a silent threat. Small variations in load balance, caused by bulls leaning during a climb, or suddenly shifting at a breaking point, can overload one side of a suspension, causing microfractures over time. If not recalculated and redistributed regularly, these stresses accumulate. A trailer might look intact, but its core is slowly weakening. And when you're dealing with live cargo, that weakness becomes risk. For the animals, for the road, and for the people operating the system. This is the hidden layer of bull transport, the structural intelligence working beneath the surface. The principles may come from shipyards and naval blueprints, but the reality is rural. Highways, border crossings, uneven roads. In this landscape, every movement is a variable and every decision is a calculation. To carry a herd across a country, across a continent without loss, without injury, without collapse, it's not brute force. It's precision. It's engineering. It's a system in motion, where biomass becomes ballast, and the logic of the sea now rides on wheels. And that's just the beginning of the journey. Because what happens inside the trailer, what fills the air, how the animals breathe, how they behave under stress, will soon prove to be just as decisive as the mechanics that carry them. Inside a livestock trailer, the temperature isn't set by the weather, it's set by biology. At first glance, the ventilation systems used in bull transport seem adequate. Fans circulate air, openings allow crossflow, and internal temperatures are monitored. But this setup hides a critical miscalculation. Most ventilation designs are based on external climate assumptions, as if bulls were passive passengers rather than metabolic engines. In reality, each bull is a walking furnace. Over the course of a 12-hour journey, their rumens, the microbial reactors inside their stomachs, begin a fermentation process that generates not just heat, but concentrated CO2 and ammonia. The result is a sealed microclimate that no fan timer can predict. This invisible atmosphere becomes the second environment the bulls must survive in. Without accounting for internal gas accumulation, traditional systems create a toxic buildup. Air that circulates may still be warm, but it's no longer breathable. The flaw isn't airflow volume. It's the assumption that all gases behave the same. That's why a new generation of transport systems is shifting away from fixed ventilation cycles and toward something smarter: zonal gas sensors. These sensors detect CO2 concentration inside the pen, activate fans only where needed, and adjust their power based on live emissions, not on the clock. The idea is simple: respond to the animal, not to the time. And the difference is not theoretical. In controlled studies conducted in Australia, 2 identical transport routes were compared, one using fixed airflow rates, the other using reactive gas sensor logic. The temperature inside both units remained within acceptable limits, but cortisol levels, the primary marker of stress in livestock, told another story. The bulls in the fixed-rate trailers showed 3 times higher stress indicators. They were breathing the same air temperature, but not the same air. What was missing was metabolic ventilation, not climate control. This insight has been confirmed in the field. In the Brazilian state of Mato Grosso, a cooperative that transports over 4,000 bulls per month began transitioning from conventional ceiling fans to sensor-triggered axial turbines, tuned to local gas levels instead of ambient heat. Within 6 months, on-road mortality dropped from 3.2% to 0.6%. The investment was minimal. The impact was structural, because what changed was not just hardware, it was philosophy. The system no longer treated the air as a constant. It treated it as a living, shifting substance, shaped by the biology inside the trailer. That's the core of the lesson. The stomach is the heat engine. Every animal inside that trailer is producing gases that transform the internal climate hour by hour. And yet, most ventilation still operates as if the only variable is the weather outside. But bull transport isn't static cargo. It's a reactive biome in motion. If the air doesn't adapt to it, it turns against it. Designing ventilation for external conditions is no longer enough. It's not the sun that suffocates bulls in transit. It's their own metabolism, trapped inside a design that doesn't listen. A trailer is not just a container. It's a behavioral arena. Every curve, every wall, every meter of space influences how bulls behave in confinement. And when dozens of dominant animals are placed together, separated only by steel and sound, what seems like empty structure becomes an invisible script for aggression. Traditionally, most livestock compartments are built in rectangular form. Efficient, stackable, easy to manufacture. But this design carries a hidden flaw. It creates spatial traps. Dominant bulls, when cornered or visually fixated on others, become territorial. They lunge, block, or crowd. The corners become pressure points. And when the vehicle moves, accelerates, brakes, turns, those reactions magnify into injury. The problem isn't just animal temperament, it's geometry. Straight lines and right angles create areas of visual fixation, where one bull locks eyes with another, with no path to de-escalation. Rounded corners, on the other hand, diffuse those visual fields. Movement becomes fluid, not confrontational. Recent innovations in pen design have moved away from strict squares and toward curvilinear compartments with offset entrances, structures that interrupt direct sightlines and redistribute animal flow during motion. The result isn't just less conflict, it's measurable change in survival. In comparative trials between rectangular and rounded pens, researchers recorded a 47% drop in stress-related injuries, with identical bull density and transport conditions. The pens weren't larger. They were just shaped to reduce the tension zones created by edges and angles. This isn't about giving more space. It's about giving less opportunity for conflict. The stress didn't disappear, but it no longer had a target. Some operators are already applying this insight at scale. In Uruguay, a major livestock exporter redesigned its entire fleet of trailers with modular pen dividers, rounded corners, and curved visual pathways. These changes weren't cosmetic. After a full season of operation, they reported an 11% increase in average meat quality index, a score that reflects bruising, muscle tension, and stress biochemistry post-transport. No medication, no additional space, just geometry. Because when the cargo is alive, physics and psychology intersect. Bulls are powerful animals, but they are also reactive. They respond not just to other bulls, but to the environment that frames those interactions. The insight is counterintuitive. Aggression doesn't rise with density alone. It rises when design fails to manage perception. Dominance is triggered in sightlines, not in square meters. And so the path to safer transport isn't wider pens. It's smarter flow. Curves, not corners. Movement, not confrontation. And a design that speaks the language of instinct, not resistance. What if the most important advancement in bull transport isn't a stronger trailer, a faster route, or a tougher axle, but an algorithm? For decades, livestock logistics was shaped by the physical. Vehicle design, fuel range, ramp angles, suspension systems. And for good reason. You're dealing with animals that weigh over 600 kilograms each, capable of sudden, forceful movement, and highly sensitive to environmental stress. But in recent years, the challenge has shifted. Not because the animals changed, but because we've begun to see them differently. Not as passive cargo, but as living systems, whose behavior, physiology, and collective dynamics must be monitored, predicted, and responded to in real time. Just as modern agricultural machinery, like variable rate seeders or autonomous sprayers, adapts to micro-variations in soil and topography, the new wave of livestock transport adapts to biological signals in motion. It's not enough to ensure bulls arrive intact. The goal is to ensure they arrive stable, uninjured, reproductively viable, and market-ready. And to do that, operators are no longer relying solely on mechanical robustness. They are turning to predictive technologies that understand what happens inside the trailer, moment by moment. In Saudi Arabia, one of the largest live cattle shipping terminals in the world has adopted a system that quietly redefines what it means to transport animals. Before a single tire rolls, the trailers are equipped with AI-assisted motion recognition systems, infrared sensors, thermal cameras, and vibration detectors that map movement patterns in real time. But the goal isn't just to detect whether bulls are standing, lying, or crowding. The goal is to interpret patterns of agitation, pacing, sudden shifts, group clustering, or micro-vibrations that precede aggression or collapse. These aren't alarms. They are signals. And once detected, they activate a cascade of adaptive responses. If the system detects early signs of crowd stress in the rear quadrant of a compartment, humidity levels are adjusted locally, not globally. Light exposure may dim in specific zones, reducing stimulation. In some trailers, low-frequency ambient sounds, carefully selected, are modulated to slow heart rates. Ventilation fans, no longer operating on timers, are driven by gas concentration readings and animal heat signatures, not air temperature alone. And crucially, this doesn't happen at intervals. It happens continuously, without interrupting the driver, without waiting for visual cues. It's a closed-loop system, calibrated to biology, and the results are striking. After a full season of operation using this system, the terminal reported a 36% decrease in injuries, alongside improved post-transport fertility metrics in bulls destined for breeding programs. These are not just animal welfare statistics, they are economic indicators. A calmer bull is a safer investment. A stress-free bull converts feed better, bruises less, recovers faster. In logistics terms, this is about reducing shrinkage. In biological terms, it's about protecting integrity under motion. But perhaps the most profound shift isn't technological, it's conceptual. For the first time, the logistics of moving bulls is approaching the language of systems biology, not just mass on wheels, but intelligent, self-regulating cargo that signals back, cargo that demands interpretation. And in response, machines are evolving not to overpower, but to listen. The future of livestock transport won't be defined solely by steel frames and diesel engines. It will be defined by data loops, behavioral analytics, and predictive adaptation. Because transporting bulls is no longer just a test of force. It's a question of how well we can anticipate the behavior of a living load and build systems that evolve alongside it. The new frontier is not strength, it's sensitivity, not reaction, but foresight. A truck may still carry a herd, but inside it operates like a neural network, interpreting signs, correcting rhythms, and silently tuning itself to the pulse of every animal on board. And that may be the greatest achievement of all. Not just moving millions of bulls across continents, but doing so in a way that respects what they are. Not units, not cargo, but complex biological systems in motion.